In this lecture, we'll introduce a new estimation approach called instrumental variable approach. Let's first review what we have done so far for causal model estimation. So far, we have talked about two methods for estimating a causal model. One is simply running an OLS regression of the dependent variable on the vector of causal variables. And this simple method is suitable, gives us consistent estimator for the parameter of interest, beta 1, if the causal variables are randomly assigned. Or in other words, or the precise condition that we need is for the error term to be orthogonal to all of the causal variables we are interested in, we include in this causal model. So if random assignment or randomized control trial is a way to guarantee this orthogonality condition, and is a way to make sure that an OLS regression of y on x give us a consistent estimator for beta 1. Now that's the first approach. But of course, oftentimes random assignment is not satisfied. But more often, we are able to justify conditional random assignment of the causal variables x given a vector of control variables. So this is the form of the conditional random assignment assumption that we give. If this conditional random assignment assumption is satisfied, that is, given W, x is no longer relevant for you. Given W, x is randomly assigned. And if we also assume EU given W to be linear, then the control variable regression of that is the OLS regression of y on x and the control variable W will give us a consistent estimator for the causal effect beta 1. So we talked about two approaches, OLS regression of y on x, which is suitable when x itself is randomly assigned, and control variable regression, which is when you add the control variables to the OLS regression. And that is suitable when x is conditionally random assigned given W and some functional form assumption is satisfied for the error term. And this functional form assumption, we talked about that a couple of times. That is not so crucial because you are free to choose a flexible functional form for this function by adding different nonlinear terms of W to relax it. But the conditional random assignment is key for the control variable approach to work. And this control variable approach can be justified in some randomized control trial when the treatment is not completely random assigned, but assigned according to some observables. And more often, it is justified in non-experimental data when you can tell a story about how X is generated. And in that story, you make it credible that X is generated by W and some completely random idiosyncratic noise that is not correlated with the unobservable factors in the U equation. Okay, so these are the two approaches we talked about. But if you cannot justify either of those assumptions, then these methods do not give us consistent estimators for the causal effect beta 1. And today we're going to discuss another method that's called the instrumental variable method. It will take all the lectures left of this semester for us to finish discussing this instrumental variable method. So what is the IV method? Not this kind of IV, of course. So to start talking about IV, let's get started with a simple causal model, let's get back to the simple causal model where there is only one causal variable and one causal parameter of interest that we want to estimate. And as always, the error term in the causal model summarizes all the contributing factors other than x to y. And we normalize u to have expectation 0. So those are standard. Now, what is an instrumental variable? An instrumental variable is a random variable that is correlated with x, but not correlated with u. So both of these requirements are crucial for the definition of the instrumental variable. So the instrumental variable, we denote it by v, standing for the v in the instrumental variable. Instrumental variable v should be correlated with the causal variable and not correlated with the other factors, the unobservable factors in y. Okay, so that's the key. So suppose you want to estimate the return to education. When x is education, y is wage, and u is other things that contribute to wage that is not education, then an instrumental variable should shift education, should be correlated with education, but should not be related to any of the other factors affecting y. Okay, so if you believe the main thing in the error term is intelligence, then the instrumental variable should have nothing to do with intelligence of the individual, okay? But should still be able to move education. So that's the idea. Now, how does this kind of variable help us? How do we use such a variable? Once we have a variable like this satisfying these assumptions, how do we use it to obtain a consistent estimator for beta 1? To see how it helps, let's first do some mathematical exercise. Let's project x on v. So projection of x on v, we project x on v, meaning that we find a linear function of v that's the best linear approximation for the expectation of x given v. So we project x on v. Suppose that projection is this, gamma 0 plus gamma 1v. And let epsilon be that projection error, meaning that that's the difference between x and the projection of x on v. So it's the difference between x and its projection on v. And from what we have learned about projection in earlier lectures, this projection error should be orthogonal, is by definition orthogonal to this variable v, okay? So epsilon is orthogonal to v. So E epsilon is 0 and E epsilon times v is also 0 by the definition of projection. We learned that in lecture 1 after the midterm exam. So the idea is that now we have a projection and we have the projection error. We can rewrite x in terms of, so we can rewrite x in terms of the projection and the projection error, right? By definition, this equation holds. And now we're gonna call this projection xv. Just we define a new random variable called xv, x sub v, to be gamma 0 plus gamma 1v, to be this projection of x on v. So xv, clearly it's a linear function of v. It's a non-random linear function of v. So because v is orthogonal to epsilon, this whole linear function of xv must also be orthogonal to epsilon. That's easy to see, right? Because exv epsilon equals e gamma 0 plus gamma 1v times epsilon, and that is e gamma 0 epsilon plus gamma 1 v epsilon, and that equals e gamma 0 epsilon plus e gamma 1 v epsilon. And now gamma 0 is a constant, is non-random, so that can come out of the expectation. So what we have is, here is gamma 0 times e epsilon. So that's gamma 0 e epsilon plus, same thing here, gamma 1 comes out. So that's gamma 1 times e v epsilon. And both of these are zeros by the definition of epsilon, because epsilon is the projection error of x on v. So it is orthogonal to v and has expectation 0 itself. So that whole thing is 0. So what that means is x now has been written in terms of the sum of two parts, and the two parts are orthogonal to each other. So x has been decomposed into two orthogonal parts, two additive orthogonal parts, right? So x has been written into xv plus epsilon, where xv and epsilon are orthogonal, have zero correlation, zero covariance. Okay, so now we have this. Now we have decomposed the x into these two parts, and we're going to analyze these two parts. We're treating them as if we observe them, even though we don't. All right, so let's treat them as if we observe these two random variables. As you can see, xv is a linear function of v, and v is exogenous, meaning that v is not correlated with the error term in the y equation. So v is exogenous. That is because v is exogenous. V is exogenous, which is assumed from the very beginning. We assumed that we had a random variable v that satisfies exogeneity condition, which is EU v equals 0. So exogeneity of v means that v is not correlated with the error term in the y equation. So this u is also called the structural error. So that is what we assumed from the very beginning of this analysis, EUV equals 0. And because xv is a linear function of v, it must follow that exv times u is also 0. So xv is also orthogonal to u. So xv, if we have this random variable, it is an exogenous random variable. So expectation of this sum is expectation of gamma 0 u plus gamma 1 v u, and that is gamma 0 eu plus gamma 1 e v u, and that is 0 because we normalize eu to 0 and we assume v is exogenous. All right, so that's what we just derived. So exvu equals 0, xv is part of x, and it is orthogonal to u, it's exogenous. So x itself is not exogenous, but this part of x is exogenous. Okay, that's what we have derived. So what we are saying is that we, using the instrumental variable v, we were able to decompose X into two parts, and one part is the good part of X. That's the exogenous part of X. Well, the other part obviously is going to be the bad part of X, because otherwise X would be all good. But X is not exogenous, and that's why we were not able to just run an OLS regression of Y on X to get a consistent estimator of beta 1. Right? So the epsilon part may be correlated with U, so that is the bad part of X. Now, recall our causal model to be this. We have that X is decomposed into XV plus epsilon. So Y can be written as beta 0 plus beta 1 XV plus epsilon plus U. Okay, so or if we do more algebra, that becomes beta 0 plus beta 1 XV plus beta 1 epsilon plus U. So this is exactly what we got. We plugged in X equals XV plus epsilon here, and we obtain this. Okay, so now let's treat this thing as the aggregate error term, the new error term, and treat this as the new regressor. Okay, so we call that the combination of these two errors as U star. Then now we have a different representation for Y. Now it's represented in terms of this good part of X as well as this new error term. Now this good part of X, in fact, is going to be orthogonal to U star, because this is because X, this good part of X times U star equals beta 1 E XV times epsilon plus E XV times U. And because epsilon is the projection error when you project X on V, and XV is a linear function of V, so that is, this expectation is 0. We have derived that. And we have also derived that XV is exogenous, so that is also 0. So that means this XV is in fact orthogonal to U star. What does that mean? That means if you did observe XV, then running OLS regression of Y on XV will give you a consistent estimator for beta 1. Which is the coefficient for XV in this equation. Okay. So that's what I said. If you were able to observe XV, we could run OLS regression of X on XV to consistently estimate beta 1. But of course, there is one problem, that is XV is not observed. XV is something that we constructed using the IV, using the instrumental variable. So it is not observed. However, that's not a huge problem, because by definition, XV is the projection of X on V. Projection can be written in this form. It's a linear function of V with some coefficients gamma 0, gamma 1. Projection is the easiest model to estimate. We can always estimate the projection coefficients consistently using ordinary least square. All we need to do is to regress X on V, run an OLS regression of X on V, we are going to get a consistent estimator for gamma 0 and gamma 1. So that suggests we can do the following 2 steps. In the first stage, we regress X on V to obtain gamma 0 hat and gamma 1 hat, which are consistent estimators of gamma 0 and gamma 1, the coefficients in this projection. And this will give us an estimate for an estimated version of X sub V. We call that X hat sub V. And in the second stage, we pretend that this X hat sub V is XV and run OLS regression of Y on this X hat sub V. There is good reason to believe that this is going to give us a consistent estimator for beta 1 because X hat sub V and XV are only different because these X hat use the gamma hat instead of the gammas, but gamma hats are consistent estimators of the gammas. So this step looks very reasonable from the analysis we have done. And in fact, that is the method people use to consistently estimate beta 1 when they have an instrumental variable. And because this approach ran OLS twice, this is called the 2-stage least squares because you do a least squares, minimize the squared sum of square residual. You do a least square twice, so that is called a 2-stage least squared. Okay, so this whole approach is called 2-stage least squared. The estimator coming out of this 2-stage is the 2-stage least squared estimator. All right, so that's how the 2-stage least square estimator is motivated. Now, before we talk more about 2-stage least square, so you can look at this graph for a little, this picture for a little bit, and if you live in Madison, you can expect 2-stage of winter. And it's good to prepare you, to be mentally prepared for these 2 stages. Anyway, so let's do some discussions of the 2-stage least square estimator that we just introduced. We're going to state without proof. The proof is not hard, but involves quite a bit of matrix algebra things. So we're not going to do the proof in class or in problem sets. So we're not going to even require that. But we state without proof that the 2-stage least square estimator we just defined is consistent if the conditions for IV are satisfied. Clearly, the exogeneity condition of IV should be satisfied. So the IV, V is the instrumental variable. The instrumental variable should not be correlated with the structural error, the error in the Y equation. So instrumental variable should be exogenous, and it should be relevant also, should be correlated with X. Okay, if these 2 conditions are satisfied, and if you have the IID sample, you have relevant no outlier condition, then the 2-stage least square estimator is consistent for the causal effect beta 1. So consistency is useful. As we said, we may also need some kind of distribution for the estimator. It's good to know that 2-stage least square estimator is also asymptotically normal, just like the OLS estimator. And we are able to estimate the asymptotic variance of the estimator using stata command. If you are doing 2-stage least squares, you should not literally manually run the 2 OLS regressions as is described on the previous page. Instead, you should use this IV regress command. This IV regress command will give you the same estimator for beta 1 as doing these two stages manually. But doing these two stages manually will not give you the right standard error for the estimator. The reason that doing these two stages manually doesn't give you the right standard error is because doing these two stages manually in Stata will not give you the right standard error, because in the second OLS regression you run, Stata treats x hat v as a naturally generated random variable from reality, but in fact, this variable is not a naturally generated random variable. Instead, it's something that you constructed using the sample already. And these errors in gamma hat messes up how the standard error should be calculated for your final estimator. So that is why, even though these two stages is useful for you to understand the two-stage least square estimator, you should not do it to actually calculate the standard error or do testing based on the two-stage least square estimator. Instead, you can use the IV regress command, which get you the right estimator as well as the right standard error. And the IV regress command is quite simple too. You tell Stata y is the dependent variable, x is the causal variable, and v is the instrumental variable. Of course, you also want the robust standard error option. Okay. So that's the syntax in Stata. You put x equals v inside a parenthesis, just telling Stata that this is your first stage regression. Okay. Now let's talk a bit more about the IV assumptions. These are the two crucial conditions that qualify a random variable as IV, making sure that the two-stage least square estimator is consistent. These two conditions are the relevance condition and the exogeneity condition. Relevance condition says that the causal variable x should be correlated with the IV, and the exogeneity condition says that the structural error u should not be correlated with the IV. So we already know why the exogeneity condition is useful, right? Because it would, if V is exogenous, it helps us to separate X into two components, two parts, one good part and one bad part. Why do we need the relevance condition? Why do we need the instrumental variable to be correlated with X? Suppose that the IV is not relevant. So covariance of X and V is 0. If that is the case, then when you project X on V, you're gonna get a constant, right? Remember the projection of X given V has a slope coefficient gamma 1 that is the ratio of the left-hand side variable and the right-hand side variable divided by the variance of the right-hand side variable. So if the covariance between X and V is 0, then the slope coefficient in the projection expression is 0. So the projection is only equal to only the intercept. So that means the projection is a constant. If the projection is a constant, when you run an OLS regression of y on that variable or an estimated version of it, that's going to be problematic. You run into multicollinearity problem. So it might still be, in fact, in practice, because x hat sub v and xv are not the same, there is some estimation error in the x hat version, in the hat version. Stata might still be able to execute your IV regress command. Your second stage may still run, but the resulting estimator is going to be garbage. It's not going to be consistent. And it's inaccurate and in finite samples. Okay, so you should really make sure that the instrumental variable is relevant. There should be a good story to say why the IV and the causal variable are correlated. Crucially, I also want to talk a little bit more about the exclusion restriction, which says the IV, the instrumental variable, should be not correlated with the error term U, with the structural error term U. This implies a few things. One is that V should not be assigned according to any of the omitted factors in the causal model. And V should not affect any of the omitted factors in the causal model. So suppose the factors in the causal model include intelligence. V should not be anything that can affect intelligence or be affected by intelligence. And V and intelligence should also be not affected by a common factor, because all of those can cause correlation between error and the instrumental variable. So instrumental variable should be chosen very carefully. Now let's consider an example of an IV. In this example, we again return to randomized control trial that we talked about before. Randomized control trial in clinical study is usually a randomized control trial in clinical study works very well when the treatment can be perfectly monitored. However, whenever you run an RCT in a social or economic setting, you run into the problem of partial compliance. For example, we talked about this moving to opportunity experiment, where people are given vouchers to help them move to a better neighborhood. People can be given the vouchers. The vouchers are randomized. People can be given the vouchers, but it is illegal to force people to move or to force people who are not given the vouchers not to move. So people who are given house vouchers may or may not use it, and people who were not given house vouchers may still get to move. So it is, so this problem is called partial compliance. We talked about this as a potential problem for randomized control trial. With partial compliance, the variable of interest in the MTO example is moving. Moving is not randomly assigned. So moving is still an endogenous choice of the individual. Okay, so the causal variable of interest, moving, is endogenous because it was not randomly assigned. However, we have something that is randomly assigned. That is the housing voucher in the MTO experiment. Okay. The housing voucher assignment is not equal to moving. Okay, so D is moving. It equals 1 if the individual moves to a non-poor neighborhood and 0 otherwise. Moving is what we care about. The effect of moving is what we care about. Our causal model is y equals beta 0 plus beta 1D plus U. We really care about moving, the effect of moving to a non-poor neighborhood on the welfare of the person. But because moving is not randomly assigned, moving is individual choice, it is correlated with U. So, but we do have something, we do have a V that is randomly assigned. So in this setting, because V is randomly assigned, V and the structural error term U is uncorrelated. Okay, the structural error U, if you take the potential outcome framework, U is the potential untreated outcome, and that is uncorrelated with voucher assignment, because voucher was randomly generated. So the voucher assignment dummy variable is exogenous, satisfies the exogeneity condition. And also the voucher gives people money if they move, so that makes it substantially cheaper to move. Therefore, it is credible that the instrumental variable is also relevant for moving. So this variable V, the voucher dummy, satisfies the two conditions required for an instrumental variable. So it can serve as a good instrumental variable. So you can use this voucher to estimate the causal effect beta 1 through to state least square. In Stata, you use the IV regress command, using tell Stata y is the dependent variable, D is your treatment, D is your causal variable, and V is the instrument. Okay, so you can do this and obtain a consistent estimator for the causal effect. Okay, so that's an example. Let's now consider another example. In this second example, suppose that we are studying the effect of a job training program on wage. So wage Y is the dependent variable, and D is the causal variable of interest. D is the dummy variable that equals 1 if the person participated in the training program, and D equals 0 otherwise. And here we take the potential outcome frameworks. U is the potential untreated outcome minus its expectation. And beta 1 is the causal effect of the training program. And I forgot to mention, but I want to stress now that for this lecture and next, we have gone back to the homogeneous treatment effect case. So beta 1, the treatment effect is now not random. So everyone in the population has the same treatment effect. Treatment has the same effect on everyone. And we want to estimate that homogeneous treatment effect. Suppose that the assignment of the treatment, that's the training program, is according to a computer-generated random number R, as well as an IQ score W. And suppose there is perfect compliance. So now the assignment of training is no longer completely random, but also is affected by an IQ score. Okay, so D, let's say, equals 1 if R plus W is greater than 0 and equals 0 otherwise. Okay, so this particular functional form is not very important. I'm just trying to give you an idea in which the treatment assignment is according to both an idiosyncratic noise and something else, some individual characteristics that might be correlated with the error term U, the potential untreated outcome. So D is assigned according to these two things. And clearly, because IQ is correlated with potential untreated outcome, D is not exogenous. So D is not exogenous. So D is endogenous. So D is endogenous. Now suppose that both R and W are observed in a data set. So both R and W are observed. Which variable is a good instrumental variable? So that's the question. Well, we can look at them one by one. We can first look at R. Does R satisfy the exogeneity condition? Oh, yes, it does, because it is a computer-generated random number. It's not generated according to anything that's maybe related to the individual. So R satisfies the exogeneity condition. And is R also relevant for D? Does R, higher value of R, make D equals 1 more likely? Well, clearly it does. Look at this, right? Higher value of R makes D more likely. So it also satisfies the exogeneity condition. It satisfies both conditions required for instrumental variable, therefore it can serve as a good instrumental variable. Now what about W? W, in fact, is not a good IV. It should not be used as an instrumental variable. First of all, it doesn't satisfy the exogeneity condition. W is the IQ, and IQ is very much correlated with potential untreated weight. Okay, so W is not a good IV because exogeneity condition fails for W. So in this example, you can use R as the instrumental variable. Okay, sorry, too fast. You can use R as the instrumental variable to do a two-state least square regression, or IV-reg in Stata, to consistently estimate beta 1. Okay, so what you would do is IV-reg Y D equals R. Now let's modify example 2 a little bit and see what happens. Suppose it's the same example, except now we have partial compliance. When you have partial compliance, we use a different symbol to denote this assignment of the training program, because D, participation, is no longer the same as assignment. People assigned to the training may or may not receive the training. So let V denote the assignment dummy equals 1 if the person is assigned the training and 0 otherwise. And let D was the participation dummy. And participation is not the same as assignment because there was partial compliance. but still assignment still makes participation more likely. Okay, so V equals 1 is still makes D equals 1 more likely. So there is a positive correlation between V and D. When there is such partial compliance, is R still a good IV? Well, the answer is yes. Even with partial compliance, this computer-generated random number is still a good IV. Okay, so this computer-generated random number is still exogenous because it was still generated according to something unrelated to potential untreated outcome. And also it's still relevant because R, higher value of R makes V equals 1 more likely, and V equals 1 makes D equals 1 more likely. So therefore R and D are positively correlated, and that makes the relevance assumption still hold. So UR is still 0, and the covariance between R and D is still non-zero. So that's another example where you can use an instrumental variable. Next, I want to talk about an extension to the instrumental variable approach just discussed. In this extension, the exogeneity condition may or may not hold, but a conditional exogeneity condition holds. Okay, we're gonna assume a conditional exogeneity assumption instead. So what's conditionally exogenous IV? So what are conditional exogenous IVs? Now, still consider this causal model with one causal variable and an arrow term U that summarizes all the other factors. Now, suppose that a variable V satisfies a conditional exogeneity condition given a vector of control variables V. Mathematically, that condition is stated as this. That's the projection of U on V and W equals the projection of U on W only. That is, once you project U on W, what's left is not correlated with V. Okay. And also, we not only need the exogeneity condition, we also need the relevance condition. We are also going to have a conditional version of the relevance condition. That is, when you project X on V and W, V here is not redundant. That is, after projecting X on W, what's left is still correlated with V. Okay. So V is relevant for X even after being projected on W, after taking out a linear function of W. Well, U should not be correlated with V after taking out a linear function of W. Okay. So if these two conditions are satisfied, then we can use V as an instrumental variable while using W as a control variable. Let's see how we can use V and W to come up with a consistent estimator for beta 1. To motivate the estimator, we're gonna project both sides of the causal equation. Remember that is beta 0 plus beta 1x plus U. We're gonna project both sides on V and W. right? The way we use control variables is to add it to the projection, right? So we project the y on both v and w. We get beta 0 plus beta 1 times, was I using x or d? So it should be x. I'm mixing up the notation here. All right. Now after projecting, so now we project y on v and w. That projection equals beta 0 plus beta 1 times the projection of x on v and w plus projection of u on v and w. Now, by the conditional exogeneity of v given w, the v here in the projection of u given v and w should drop out. So this conditional exogeneity implies that this v can drop out. Right, so projection of y given v and w can be written as beta 0 plus beta 1 projection of x given v and w plus projection u given w. All right, so now we have used conditional exogeneity of v. The next thing we're going to do is to define the projection of x given v and w. That is a scalar random variable. We define that to be, even though v and w vector form a vector, the projection of x on v and w is of the same dimension as x, which is a scalar. So therefore, that is a scalar random variable. And that we define that projection to be x sub vw. So that is the part of x that is picked out by v and w. Okay, so x sub vw. We define that, and also we read out the projection of u on w as gamma 0 plus gamma 1 prime w. Now we plug both of these in that equation, and what we are going to get is this. So projection of y given v and w will be beta 0 plus beta 1 x vw. So that's x x vw plus gamma 0 plus gamma 1 prime w. Now we put beta 0 and gamma 0 together. Okay, and we can write projection as beta 0 plus gamma 0 plus beta 1 dvw plus gamma 1 prime w. Or in other words, if you define u star to be the difference between y and this projection, then y can be written as this function. Here, u star is defined to be y minus the projection of y given v and w. Now, that becomes interesting because by definition of projection error, the projection error should be orthogonal to the conditioning variables. So it is orthogonal to v and orthogonal to w and has mean 0. So therefore, you can estimate all these coefficients in this projection equation by running OLS of y on dvw in w. That is, if you observe d sub VW. Okay. So if you do observe d sub VW, you can regress y on d sub VW and W. And that will give you a consistent estimator for beta 1. So the coefficient from that regression, that OLS regression, the coefficient on d sub VW from this OLS regression is a consistent estimator for beta 1 for the causal effect. Okay. But of course, d sub VW is a projection that we do not observe. However, estimating projection is not difficult. We can do a two-state least square. In the first stage, we regress d, actually it's x, but I keep calling it d. So just in your mind, imagine d is x. So in the first step, you just regress this causal variable on V and W and get an estimated version of x sub W. Let me change all of this to x so that we are not too confusing. All right. So in the first stage, you run an OLS regression of x on at V and W, the instrument and the controls, and get an estimated version of the projection of x on V and W. And in the second stage, regress y on this estimated version of x, of the good part of x, as well as the control variable, the control variables. Okay. So let me also correct all these d's. Okay. All right. Okay, so that's how you use a conditionally exogenous instrumental variable. And you can also see from here that the conditional relevance assumption is useful, because if the conditional relevance assumption is not satisfied, then XVW will be only a linear function of W. V will not enter there because the conditional relevance assumption is not satisfied. Then this is a linear function of W. And that will be perfectly collinear with this W vector. And perfect multicollinearity almost always never work. Okay, so even so the two-state least square will become inconsistent because of this. So that this is why the conditional relevance assumption for the instrumental variable V is also important. All right, so that is using two-state least square, that is using a conditionally exogenous instrumental variable. And we state without proof that the two-state least square estimator we just described consistently estimate the causal effect. So let me also correct this one. All right. In Stata, clearly you still cannot, should not run the two OLS regressions manually, because even though that gives you the correct estimator for beta 1, it doesn't give you the correct standard error for that estimator. So instead, you should use the IV regress command. When you use the IV regress command, what you do is the following. You tell Stata y is the dependent variable. And inside the parentheses, you tell Stata this is the endogenous variable, and V is the instrumental variables. And you write the control variables outside this parentheses. Okay, so these control variables are outside this parentheses. An equivalent way to do this in Stata, you can equivalently do, this is going to give you exactly the same result. You can do IV regress, y x equals v, w, you can put the w's inside the parentheses as well. And both will give you exactly the same answers. Now, let's talk a little bit about the IV conditions. We actually already talked about it. For the case where we have control variables. So note that the two-state least square we just introduced will only work under these two conditions, under the following conditions. The first condition is a conditional relevance. That is, the projection of X on V and W actually contains V. So this delta 1 is the delta coefficient on V in this projection. So the projection, if you write the projection as delta 0 plus delta 1V plus delta 2 prime W, then this delta 1 should be non-zero. If delta 1 is 0, the conditional relevance assumption is not satisfied. And the second condition we require clearly is conditional exogeneity. That is, projection of U on V and W should not have a V in there. Okay, the V should not be in this projection, should not appear in this projection. All right, so these are the conditions. Now let's consider an example. In this example, this is actually the same example as the one that we talked about before discussing conditional exogenous IVs. But there is a twist. So still the causal model is y equals beta 0 plus beta 1d plus u. And d is the causal variable of interest. We run a randomized control trial, but D cannot be randomized. So D is the job training program. So the D is the dummy variable for participating in the training. And V is assigned to training. The assignment V can be randomized, but D is not equal to V. That is, there is partial compliance. There is partial compliance, and we discussed right before introducing conditional exogeneity that This R, the computer-generated random number that we use to assign the training program, R would be a good IV because R is exogenous and R is relevant for D. However, now let's assume that R is not observed. R is unobserved now. Okay? So if R is unobserved, clearly we cannot use it as an IV because it's not observed. What are we going to do? Now, let's look for other IVs. So is W a good IV? W is IQ. It clearly is not a good IV because it doesn't satisfy the exogeneity condition. It's correlated with the potential untreated outcome. And V clearly is also not a good IV because V is correlated with U because of W. So V is not exogenous. D clearly is also not exogenous. Participation is a personal choice, and personal choice may be related to other personal characteristics that affect Y. So none of the observables are good IV are exogenous. Looks like we're doomed. However, we are not, because conditional on W, V is only variable because of R. So once you are given the value of W, V only varies with R. And the variation of R is completely exogenous because R is a computer-generated random number. So V, in fact, satisfy a conditional exogeneity condition. It's conditionally randomly assigned given W. That is, expectation of U given V and W equals expectation of U given W. Okay, so in fact, we have a stronger condition than this. We have that given W, given the value of W, there is only R left. R is independent of U. Okay, so therefore this conditional random assignments is satisfied. If in addition, we assume, we're going to talk about this additional assumption later. If in addition, we assume that EU given W is linear in W, and because EU given V and W equals EU given W, so EU given V and W is also this linear function of W. That is, EU given V and W is also linear in W, and V doesn't appear here, so you can write that as a function of V, but V has a 0 coefficient. So that is also linear in W and V. So when conditional expectation is linear, projection equals conditional expectation. So projection equals this conditional expectation, which equals this conditional expectation without the V, and which equals this projection without the V. Therefore, the projection version of the conditional exogeneity that we assumed is satisfied. And that implies that V can be used as an instrumental variable given W. Okay, so that means what you can do is run IV regress Y X equals V. So X is the causal variable, V is the instrumental variable, and given the control variable. Okay, so and that's the way to obtain a consistent estimator for beta 1 in this case when R is not observed. Now, let me talk a little bit about this assumption. Do we really need this assumption? Do we really need this assumption? Okay, can we simply argue that the projection of U given V and W equals projection of U given W in this example. Can we simply argue this holds because V is independent of U given W? Well, the fact that is that we cannot. This assumption so let me do this discussion. The projection of U given VW equal projection of U given W is in fact not implied by EU given VW equals EU given W, unless is linear, unless this conditional mean is linear. Why is that so? The reason that this is so, the reason that this is not implied by this is this describes how U and V should be related, how U and V are related after taking out a linear function of W. Well, this describes how U and V are related after taking out W completely. So this conditioning of W in the projection is a kind of a limited capacity. Okay, so we're not taking out the whole effect of W. Okay, only taking out W linearly. So that is why when this hold, this may or may not hold. I can give you an example, a counter example where these hold, but this doesn't. So a counter example. In this counter example, I'll just take a very extreme case, just to make it simple. In this counter example, let's say V equals W squared. Okay. If V equals W squared, then when W is given in the conditional expectation, V is completely determined. So EU given V W equals EU given W. In fact, the probability density function of U given VW equals the probability density function of U given W. This is simply because once W's value is given, the value of V is also given, and the V doesn't provide additional information. Okay. But the projection, but suppose EU given W is in fact W squared. That is possible. Say U and W are just related in this way. If EU given W is in fact W squared, then projection of U given VW, if EU given W equals W squared, that implies EU given W equals V, so it's a linear function of V, and that also equals EU given V and W, because these two conditional expectations are the same. So in fact, EU given V and W is linear in V and W, where W receives 0 weight. So projection of this equals V, equals the conditional expectation. But that is not equal to projection of U given W. Right? That's projection of U given W. What is projection of U given W? To get projection of U given W, you actually want to solve the minimization of, say, B0 plus B1W minus the conditional expectation, W squared. So you want to solve this minimization. And when you try to solve this minimization, you take the first derivative with respect to these two, you're going to find that B0 plus B1 EW minus EW squared should be 0, and B0 EW plus B1 EW squared minus EW to the power 3 should also be 0. After you solve this equation, you find it's not going to be, in fact, well, it's actually easier than that. Suppose B0 star and B1 star are the solution, then projection of U given W is B0 star plus B1 star W. And that cannot be equal to V, because V equals W squared, okay, for most values of W, unless W is of some very special form, this equation will not hold. So that is a counterexample to show that this version of conditional exogeneity, unless it's coupled also with linearity, does not imply the projection version of the conditional exogeneity. So for the example we have here, we do need this additional linearity assumption. Of course, you might ask, what if the linearity assumption is not satisfied? If the linearity assumption is not satisfied, you can relax it by adding nonlinear terms. After adding nonlinear terms to it, you can, in the two-state least square regression, you can add nonlinear terms to the control variables, to the group of control variables, just to make sure, just to make this kind of assumption easier to satisfy. Okay, so that's a bit more detail about using control variables with IVs. All right, so next week we are going to talk about 2 more examples of instrumental variables.